Guys, in this lecture module, we're going to talk about something called standard additions. And it is exactly what it sounds like it will be. You will make some standards and you will add something to them. I mean, how easier can this get, right? Give me a break. Well, it's the math that's kind of tricky, not the definition. So I've always heard stories in the past of our students going out, or our graduates at that time, going out and participating in job interviews. And some of the questions concern solution prep. They want to make sure that you fully understand, that you know what you're doing, and what some basic terminology means in a laboratory environment. And standard addition used to be something that would throw our people for a loop. We would gradually touch on it, we would do 1 or 2 labs with it, and that was about it. So now we've created a course like this one where we can devote a whole lecture module to the concept of standard additions to tell you a little bit about what it is. All right, so how can I describe standard addition? We're going to start with the theory of it first, and then we'll talk about how to do the math that corresponds to it. So standard addition, imagine a sample being brought to you in a laboratory. All right, so here is my picture of a sample, and we bring it to the lab, and we say, lab, we want to know what's in that sample. Well, up to this point, we've only talked about calibration curves. We said, okay, if you want to measure the benzene level in something, then we'll make a series of benzene standards and we'll run them and we'll do a calibration curve. And then these samples get processed with the calibration curve, right? So that would be the lab's general response. Hey, we'll do a cal curve with our set of standards, and then we'll solve for the sample in the cal curve. We'll probably need to use Excel or the software to make that calibration curve, and we're done. Well, that's great. The problem is that we make a lot of assumptions here. Well, what kind of assumptions? I'm getting ready to tell you. So the problem with a general calibration curve is that these work really well with what I would call a simple sample. Now, what is a simple sample? Right? Well, this would be something like we have always handled in the laboratory up to this point, for the most part. It is a sample with very few components. Not too many things are involved, maybe 5, 6, 7. And as long as that many components are present, then we can pretty much do a calibration curve and be okay with it. But let's say that this sample that's brought into the lab is a gasoline sample. Well, that gasoline probably has 70 to 80 components that are on the inside that make gasoline up, right? And if I analyze gasoline for one of those components, oh my goodness, 1 out of 70 to 80, it can be done. But a calibration curve is not going to be the best scenario for that. And that's why. So calibration curves are great for samples that are very simplistic in nature. If there's only a handful of things that are involved and you want to look for one of those and you want to measure one of those, or maybe all 5, 6, or 7 of them, then you can do that with a typical calibration curve. No big deal, right? We've done them before. You've made calibration curves up to this point, but notice what's happened. We've made you make a calibration curve off of one component, and that's it. That's all we've done. So what if we bring in gasoline, and this gasoline has 70 to 80, and these 70 or 80 components, let's say that I say, hey, I want you to measure for benzene. Calibration curve is not the best. So what we do is that if it's a complicated sample, we use the method of standard addition instead. Okay? That's its purpose. That's its role. it handles complicated samples very well. Now, why is this an issue? Well, you can imagine what data would look like from 70 or 80 components. It's going to be busy. It's going to be messy. It's not going to be the prettiest data or report that you're going to look at. But the assumption is that no other component will interfere. And that's where the problem is at, because we know this is not true. In a calibration curve, that sample is very simplistic, not too many things are present. This chance of interference is very low. We don't have to worry about it anymore. That's why we do a calibration curve. We do a set of 5 standards, we run them, and we call it a day. The problem is that when I get upwards of multiple components in a sample, I cannot guarantee that those other components will not interfere with the component I'm looking for. Those 70 or 80 other components in a gasoline sample, who's to say that their presence does not suppress or enhance the signal? It could go either or. Maybe there's no effect at all. But there is a chance that one of those other components, because there's a bunch of them, could interfere with benzene signal and make benzene read a little bit higher than if it wasn't there. Or that component could make benzene read a little bit lower if it wasn't there. All right. So let me say this a different way. If we have a sample that's very complicated, the complications happen because of all of the other stuff that's present. If I make a set of standards, and let's say that I am looking for benzene, and I do a set of standards, your typical 4 to 5, there's my volumetric flask, and they range in concentration. So let's say 1, 2, 3, 4, 5 part per million. And I run these and I make a calibration curve with them. And I get my general trend line. That's what we've always done. And that works. The problem is that this is benzene and a solvent. And that's it. Nothing else is present in that set of standards. So if the laboratory gives me a sample, and this sample is gas, and that sample has benzene in it, well, it's benzene and tons of other things. Like we said already, 70 to 80 other things that are present. How can that actually be apples to apples? Because in my set of standards, it's just really benzene and the solvent. That's it. But in the sample, it's benzene and 70 to 80 other things. All right, so some of the instrumentation does a pretty good job with no interferences at all, but others do not. They need a little bit of help. And that standard addition process is going to help us out with that. So how do we fix this? There's no way that you're going to tell me that I'm going to have to make benzene standards, and instead of just one solvent like methanol or acetone, I'm going to make this similar by adding 70 or 80 other things to these standards. No way. I'm not doing that. No one in their right mind would do that for each one of them. There's a better process for that. It's called standard addition, and that's what we're getting ready to talk about. In addition to that, these 70 or 80 other components we said could interfere with the signal. So pure benzene with a solvent could maybe give me some signals, and I would plot those on a calibration curve, and I would get a straight line. But this benzene, even though it's present, has 70 or 80 other neighbors, friends that could maybe influence it to do other things. And it could slightly increase or it could slightly decrease that signal. I just simply don't know how they're going to behave because the sample is too complicated to do that. So standard addition is the choice when it comes to complicated samples like this one. So in this lecture module, you're going to be learning about standard addition. You're going to be learning how to do the math with standard addition and the whole full concept of what standard addition actually is. How would we actually do it in the lab? So if I can't just simply take benzene, put it into a volumetric flask and add solvent, then how on earth could I make a set of standards that's more realistic to the sample that was brought into the lab? How can we do it? There's 70 or 80 other things in it. Well, there's a trick, and it's called thinking outside the box. So that's what you'll learn how to do in the next video. We'll learn how to think outside the box and take the sample and use it to our advantage.